I wanted to also cover, I think it's in section 3 of your book, talking about how a generator works. I want to talk about a generator simply because we use them to create electricity in so many aspects of our life. If you camp and you use a motor home or a travel trailer, you probably have had a generator. So it basically takes some gasoline, changes from mechanical energy to electrical energy so that you don't have to have a plug-in to hook up to. You can just run your generator and you can operate everything electrical in your camp trailer. Your car has a generator. It actually has a special name. We call it the alternator. What a generator does, that generator in your car, the alternator, is it is constantly spinning. It has a belt that makes it spin, and as you can see, you'll have like a core of wires. They'll spin around, and when that happens, it causes electricity, and that electricity is hooked to your battery, and that's what keeps your battery charged all the time. If you continually have a low battery or a dead battery in your car, that's one of the things to check. Your battery could actually be busted. It could be used up, no longer good. You need a new one. Or maybe your alternator isn't working correctly, therefore your battery is not getting recharged. So how a generator works, you have rotating coils of wire and they're in a magnetic field, and that creates electricity. So when we talk about electricity and we talk about magnetism and we talk about generators, because they're all intertwined, we need to talk about AC and DC current. Okay, alternating current, that means it goes in one direction and then comes back. Direct current, DC current, it only travels in one direction. An example of that would be a battery of any kind. It is a direct current, a DC. The battery charge only travels from the actual negative part of the battery to the positive. Alternating current would be like what you have at your house or here at the school. When we plug in, it's an alternating current. It means that the direction of that electrical current is always changing. So why does this matter? This is why. Because if you have an alternating current, AC, you probably are familiar with a transformer even though you don't know it. When you go home today, look up at the power lines and see if you see something that looks like kind of a large gray trash can, just a round can sitting up there by the electrical lines. That is a transformer. And in that transformer, it has a core of metal, and then it has wires wrapped around it. And those wires cause it to either be a step down or a step up transformer. So it has a primary coil and a secondary coil. So what's the difference? A step-up transformer actually increases the voltage, and a step-down transformer decreases the voltage. Now, on the power lines, you see that gray can-looking thing. That's a transformer. It's a step-down transformer. And what it does is it takes that 220 or 240 volt electricity, that high voltage in those lines, and it actually steps it down so that it can work in the 110, 120 that you have in your house. If we didn't step it down, then you'd either have to rewire your house with a higher voltage, or you'd be blowing up all your stuff if you tried to plug it in. So that's what transformers do. They make our life a little bit easier and a little bit better so that we can take electrical power and use it. Now, another interesting thing while we're talking about generators and transformers is we have some of the cheapest electrical power costs in the entire nation. One of those reasons is because we generate our electricity mostly with hydropower. We use our water. So when they let water out of the American Falls Dam and Reservoir, or they let it out of the Palisades Dam and Reservoir over by Jackson Hole, they actually run it through turbines, let gravity work for us, let it out the top. It hits a turbine which then spins, which causes this generator to spin, and it creates electricity, which they send out power lines, go to the step-down transformer so that you can charge your phone tonight so you can drive me crazy using it in class tomorrow. So that's how that all works. The Earth is a magnet. We all know that because in 1600 they discovered that. And the interesting thing about the Earth is the fact that it has this magnetic force field around it. It is strongest, just like a bar magnet, it is strongest at the poles. But we have this field that goes out. So if you'll notice, I want you to pay special attention. Here is the geographic North Pole, the place where Santa lives. It is the magnetic South Pole. Think about that just for a minute. This is, and you'll know why in a minute, that's important to know that. And the same thing happens. Here's the geographic South Pole. It's where Antarctica is. It is the magnetic North Pole. So why does that matter? Well, we'll tell you in just a second, but the first thing I want to let you know is they have guesstimated that every 500,000 years or so, our poles will switch. The magnetic north and south will switch. Now, there's all kinds of reasons that happens. It's not anything we need to go into right now. If you want to discover that and talk about that a little more, take astronomy next year or the year after. But here's the question that you do need to ponder. If they flip, does that mean Santa has to move? That's an important question because it determines what happens for our Christmas. So now, getting back to why the magnetic field matters. Okay, you have a compass. And what actually happens is the needle of the compass always points towards the magnetic South Pole. Why does that happen? It doesn't seem like that should be right. Well, if you remember, opposites attract. So in order to find north, the direction we call north, your compass actually is attracted to the magnetic South Pole. Now, the sun and all the planets also have magnetic fields. And the reason they have those magnetic fields is because they all have three things in common: iron, cobalt, and nickel. When you actually have a star, which our sun is a star, when you have a star that starts to die, there is nuclear fusion going on, and it is hydrogen that is fusing. And as they use up all the hydrogen, then they start fusing helium. And the helium changes into oxygen. And once the oxygen is fused, it actually is fusing and changing into neon. And once the neon is fused, it actually is changing and fusing into magnesium. And once it fuses, it changes and then silicon fuses. And once that happens, right before the end of the death of the star, all the silicon is fusing, and lastly, you end up with an iron core is what you have left. So every single star has a magnetic field. All of our planets that are terrestrial planets, the first 4 or 5, Mercury, Venus, Earth, and Mars, they're terrestrial, meaning they have rocks and stone and earth. They all have cores that have iron, cobalt, and nickel. And all the Jovian planets, which are the ones out from there, Jupiter, Uranus, Neptune, Saturn, Pluto, they all have a little bit of iron, cobalt, and nickel. Mostly they have a lot more gases, but they all have a magnetic field. This matters to us because the sun actually gives off magnetic waves and gives off magnetic material, and we call it the solar wind. It's actually just energy coming towards the earth. When it comes to the earth, what happens is you actually have all these magnetic fields. We saw all those going from pole to pole, and if any of that material that gets through actually hits that magnetic field, and it just starts twirling and twirling and twirling around the field, and it does something really, really cool when it spirals around like that. And we'll tell you about that just here in a second. So one of the things that happens is it hits this magnetic field, and it makes what we call the Van Allen belts, the inner and the outer Van Allen belts. Now, most of it, when it hits our magnetosphere, which is actually our magnetic field, it just hits it and kind of bounces off, goes right by it, just like a snowplow through a snowdrift. Our magnetosphere is there, and all that solar wind and that magnetic, it just goes past it. But if it gets in and it makes those Van Allen belts, then you get something really, really cool like the aurora borealis. And the reason the aurora borealis happens is because we actually have all of those particles that have gotten through the atmosphere that are really excited. And when we say they're excited, what we mean is they have picked up lots of energy. From chemistry, you should know that an atom picks up or loses energy when it loses or gains electrons. And when it does that, there's an energy release. And that's why we say that it's excited, and we get this really pretty light show in the northern hemisphere called aurora borealis. And now, if I haven't stuffed enough in your mind quick enough, I have a little cartoon for you. This cartoon shows students sitting in a class, and it shows the teacher up front, and the kid says, "Mr. Osborne, may I be excused? My brain is full." Well, we have a few more days. Don't give up. We still have to get you through the end of course assessment. I know your brain is full, and it's going to get even fuller before we hit next Thursday, but that's okay. Keep in mind, science is just describing the things you already know. We just think we've got to put special words with it or special phrases. You know this stuff. Be confident. Have fun with magnetism, and we'll see you for the review.